Assalamualaikum and hi students. So this is a lecture video for BMCG 1013 differential equations. So we are still in chapter 5, partial differential equations. The learning outcome for the second video of chapter 5 are to solve heat equation on the heated rod problem and to solve wave equation on the vibrating string problems. 5.3 we have the applications of PDE. The first application is on the heat equation for the heated rod. Okay, so one-dimensional heat equation is given by del U over del T equal to K del square U over del X square with interval X from 0 to L and T is a positive number, where the solution U is unknown function of X and T. So you have U X T and K is positive constant. Consider a heated rod length. The length denoted as L has specified fixed temperature at the two ends of the rod and temperature function Fx at T equal to 0. And then the boundary conditions are given by U when X equal to 0 and U when X equal to L is equal to 0. And the initial condition Ux when T equal to 0 is equal to Fx. Therefore, the boundary value problem is written as you have the PDE, you have the boundary conditions and the initial conditions. An example for heat equations is given by example 5.8. Suppose that a rod length 4 cm is heated with initial temperature function Fx is equal to x square and its two ends are embedded in ice at temperature 0. So T equal to 0. The boundary value problem for this is del U over del T equal to del square U over del X square. The length of the rod, so 0 to L, L is equal to 4 and T is positive. Okay, temperature is positive. And then we have boundary conditions when U when X equal to 0 and when X equal to 4, it is equal to 0. And then initial conditions U when T equal to 0, it is equal to x square. In your final exam, you'll be asked these three questions, sub-questions, okay? So A, write the separated equation as two ordinary differential equations with K as a constant. So for this one, you may have 4 marks. And then B, by using the method of separations of variables, solve the separated equations by considering all possible values to determine the general solution of UXT. So for this, you have 10 marks. Another 11 marks is from question sheet. You need to solve the initial boundary value problem for the case when K is less than 0. So let's start with A. For A, as usual, you need to start with let UXT equal to X multiplied by T. Okay, and then substitute this del U over del T with X T prime equal to X double prime T. And then divide everything with XT. Okay, you have T prime divided by T equal to X double prime divided by X. Separated equation. So the two ODEs are T minus K T equal to 0 and X double prime minus K X equal to 0. This is for A. Continue with B by using the method of separation of variables, solve the separated equations. So moving to step 2. Okay, consider the 3 cases. So case 1, when K positive, K is equal to lambda square. Okay, so substitute lambda square into K, you have X double prime minus lambda square X equal to 0. So M square minus lambda square equal to 0 roots. Okay, you have plus minus lambda. So general solution for X is basically equal to C1 exponent positive lambda plus C2 exponent negative lambda X. Okay, for T, T prime minus lambda square T equal to 0. So M minus lambda square equal to 0, we have 1m equal to lambda square, positive lambda square. And t here is equal to C3 exponent lambda square t. Once you have your x and t, you can find what is u x t by multiplying both x and t. So you have a exponent, a1 exponent lambda x plus lambda square t plus b1 exponent lambda negative lambda x plus lambda square t. Okay, so a1 is basically c1, c2, c3, and b1 is c2 dot c3. Moving to the second case. Case 2, when k equal to 0. So x double prime minus 0, x equal to 0, m1 equal to m2 equal to 0. X is equal to c4 plus c5, since it is real but repeated, so we have c5x. And then for t, you have t minus 0t equal to 0, t prime minus 0t. So m basically equal to 0, and t is equal to 6 c6. Okay, and uxt for second case is equal to a2 plus b2x. Okay, a2 is c4 multiplied by c6, and b2 is c5 multiplied by c6. Okay, continue with case 3. K is negative. K is equal to negative lambda square. Okay, so x double prime plus lambda square x equal to 0. M square plus plus lambda square equal to 0. Okay, so you have m complex conjugate. X is equal to c7 cos lambda x plus c8 sin lambda x. Do not forget your t. T prime plus lambda square t equal to 0. M plus lambda square equal to 0. M is equal to negative lambda square. And t is equal to c9 exponent negative lambda square t. uxt for third case is equal to a3 exponent negative lambda square t cos lambda x plus b3 exponent negative lambda square t sin lambda x. Okay, a3 is equal to c7 dot c9, and b3 is equal to c8 dot c9. Okay, you are done with question B. Okay, question C, solve the initial boundary value problem for the case when k is less than 0. So we just ignore the first two case. So just proceed with case 3. Then substitute the boundary and initial condition. So for boundary and initial condition, okay, from here, for this one you have x0 equal to x4 equal to 0. When you substitute x equal to 0 and x equal to 4, it is equal to 0. For this one, when you substitute t equal to 0, it is equal to x squared. So first we have x0. So you know your x. This is your x. X0 is equal to 0 means, okay, you have 0 equal to c7 cos 0 plus c8 sin 0 when you substitute x equal to 0. So cos 0 is equal to 1. Sin 0 is equal to 0. So basically you don't have this term. So you just have 0 equal to c7. So c7 is equal to 0. Since c7 equal to 0, continue the second boundary condition, x4 equal to 0. So 0 is equal to C7 cos 4 lambda plus C8 sin 4 lambda. And then C7 here is equal to 0. So 0 equal to 0. C7 is 0. Plus with C8 sin 4 lambda. Meaning that your C8 sin 4 lambda is equal to 0. But you cannot have C8 equal to 0. Because if you have C8 equal to 0, you don't have any eigenvalues. All the eigenvalues equal to 0, so you need to omit the case. But we don't want to omit this case. So set that C8 must not equal to 0. So the rest of the term, which is sin 4 lambda, must be equal to 0. As you know, sin 4 lambda equal to 0 is equal to sin n pi. Okay, because sin 0, sin pi, sin 3 pi, sin 4 pi is all equal to 0. So sin pi lambda equal to sin n pi. So you have lambda equal to 4 lambda equal to n pi. Okay, so lambda is equal to, lambda n is equal to n pi over 4. Once you have your lambda n, you need to find what is your xn by substituting lambda n into this. You need to find the general solution for x. So xn is equal to, this C7 is equal to 0. So you just have Cn sin lambda n x. So xn is equal to Cn sin lambda n x. And then substitute your lambda n. So lambda n is n pi over 4x. So you just have your general form of x. And then substitute into Tn, general form of Tn. Okay, substitute lambda here. And this C with Dn. So Tn is equal to Dn exponent negative n pi over 4 square t. And this is equal to Dn exponent negative n square pi square over 16t. You have your xn, you have your Tn, so you may have your un xt. Okay, Cn multiplied by Cn multiplied by Dn, you have Bn exponent negative n square pi square over 16t sin n pi over 4x. What is Bn? Bn is equal to Cn dot Dn. From Un, you have uxt. You can write your uxt. Okay, so you have summation. Once you convert from Un to uxt, so you have the summation, and then you have Bn exponent negative n square pi square t over 16 sin n pi over 4x. Okay, now you can substitute the initial conditions. For initial conditions, you have ux0 is equal to x square. Okay, so x square, ux0 is equal to x square, equal to summation n from 1 to infinity Bn. Substitute t with 0. So you have exponent 0 sin n pi over 4x. Okay, so you have x square equal to summation n from 1 to infinity Bn. This is equal to 1. Okay, sin n pi over 4x. In order to find the Bn, Bn is equal to 2 over L. In this case, L is equal to 4. 0 to L. Okay, and then your fx. This is fx. Fx is x square. And then just copy this sin n pi multiplied by sin n pi over 4x. dx. So basically you need to solve for 1 over 2, 0 to 4, x square sine n pi over 4x dx. And from tabular method, you have Bn is equal to 1 over 2, 1 over 2, negative 4x square over n pi cos n pi x over 4 plus 32x over n square pi square sine n pi x over 4 plus 128 over n cube pi cube cos n pi x over 4 from 0 to 4. Substitute the limit 4 and 0. Okay, once you substitute the limit, so you have this answer. So cos n pi is equal to negative 1 to the power of n. Sin n pi is 0 and cos n pi again negative 1 to the power of n. Sin 0 is 0. Cos 0 is 1. Cos 0 is 1. Okay. Then simplify this. We have this Bn. Okay. Bn to the power Bn is equal to this. And then you can substitute the Bn values into uxt. Okay. Uxt, you have this last answer. And you can substitute this. You can write this as 32 negative 1 to the power of n plus 1 over n pi as well. Okay. It's the same value. Okay. For the second application of PDE, we have wave equation, okay, from vibrating spring. One-dimensional wave equation is given by del square u over del t square equal to alpha square del square u over del x square. Okay, we have interval x and t as usual. And then alpha is a constant. Okay, consider the vibrating string problem. Thus, the boundary conditions are given as when x equal to 0, x equal to L, you have equal to 0. And then initial conditions, you have two initial conditions. The first one, ux when t equal to 0 is equal to fx. And the second one, when you have del u over del t, differentiate del u respect to t, and the t is equal to 0, so you have another function g. Okay. Last example for this video, example 5.9. Find the solution of the vibrating string problem governed by the given initial boundary value problem. Del square u xt over del t square equal to del square u xt del x square. Okay, so the length is equal to 1, 0 to 1. So the L is equal to 1. You know L equal to 1. And then from here, from the PDE, alpha is equal to 1. Subject to boundary condition. Boundary condition for this one, x0 equal to x1. x0, x1 is equal to 0. Okay. The n initial condition uxt, when t equal to 0, you have x minus x square. And then the differentiation of del u over del t, when t equal to 0, you have 2. So start with let uxt equal to xt. Okay, as usual, substitute. You have you have xt double prime equal to x double prime t divided by xt. So t double prime divided by t equal to x double prime divided by x. So the two ODEs are t double prime minus kt equal to 0 and x double prime minus kx equal to 0. Okay, for the first case, case 1, when k equal to lambda square, so x double prime minus lambda square x is equal to 0, m square minus lambda square equal to 0. M is equal to plus minus lambda. So x is equal to C1 exponent positive lambda x plus C2 exponent negative lambda x. Okay. As for t, now you have t double prime minus kt equal to 0, meaning that you have two roots for t. Okay, so m square minus lambda square equal to 0. So m is equal to plus minus lambda. So for for the general solution for t is equal to C3 exponent positive lambda t plus C4 exponent negative lambda t. Before this, in previous example, you just have t prime minus kt. You just have one root because m is 1. It's not quadratic. But now, since you have t double prime, your characteristic equations is a quadratic equation. So you have two roots and then you have this general solution for t. So u xt for first case is equal to C1 exponent lambda x plus C2 exponent negative lambda x multiplied by C3 exponent lambda t plus C4 exponent negative lambda t. Do not expand this, okay? Because if you expand this, you may have 4 terms, okay? Just proceed with the second case. Case 2, when k equal to 0. Again, you have x double prime minus 0. X equal to 0. Your two roots are equal to 0. So, m1 equal to m2 equal to 0. Real but repeated. Okay, real and repeated. So, you have C5 exponent 0 plus C6 exponent 0 x. Okay, so you have C5 plus C6x. Okay, for t double prime minus 0, t equal to 0, m1 equal to m2 equal to 0 as well. So t is equal to C7 plus C8t. Okay, then uxt is equal to C5 plus C6x multiplied with C7 plus C8t. That's it for the first two cases. For the third case, case 3, okay, k is equal to negative lambda square because k is negative. Okay, so x double prime plus lambda square x equal to 0. M square plus lambda square equal to 0. M is complex conjugate lambda I. Okay, so for complex conjugate, you have x equal to C9 cos lambda x plus C10 sin lambda x. And t double prime plus lambda square t equal to 0. M square plus lambda square equal to 0. Again, M is a complex conjugate, plus minus lambda I. So, t is equal to C11 cos lambda t plus C12 sin lambda t. So, the uxt is equal to C9 cos lambda x plus C10 sin lambda x dot C11 cos lambda t plus C12 sin lambda t. Okay, now we can continue with substituting the boundary condition. Substitute x0 equal to x1 equal to 0. So for the first boundary condition, 0 is equal to C9 cos 0. C9 cos 0 plus C10 sin 0. Sin 0 is equal to 0. Cos 0 equal to 1. So C9 is basically 0. For the second boundary condition, x1 equal to 0. 0 equal to C9 cos lambda plus C10 sin lambda, because x is equal to 1. So C0, so 0. C9 is equal to 0, so you don't have this C9. 0 is equal to C10 sin lambda. Since C0 cannot be equal to 0. So sine lambda must be equal to 0. Again, sine n pi, you know sine n pi is equal to 0. So this lambda is equivalent to this n pi. Lambda is equal to n pi. So lambda n is equal to n pi. Once you have your lambda n, substitute lambda n into this lambda. C9 is equal to 0. You have xn is equal to cn sine n pi x. Okay, and then as for the tn is equal to C11 substitute with an, capital A n, cos n pi t. Substitute this lambda with n pi, plus with bn sine n pi t. As you have xn and tn, you have your, now you can have your unx tn. Ux, simplify the uxt, you have an cos n pi t plus bn sine n pi t dot sine n pi x. Okay, an here is capital N dot cn, and bn is bn dot cn. Okay, from unt, write your uxt, the summation. So summation n equal to 1 to infinity an cos n pi t plus bn sine n pi t sine n pi x. Okay. Substitute the initial condition. Next, substitute the initial condition. Ux0 is equal to x minus x0, the first initial condition. For this one, you have x minus x squared is equal to summation n from 1 to infinity an cos n pi t when t equal to 0. So you have cos 0 plus bn sine 0 multiply by sine n pi x. Okay, so x minus x squared is equal to cos 0 is equal to 1 while sine 0 is equal to 0. So you just have an sine n pi x. Okay, now find what is an. So to find an is equal to 2 over L. L is 1, 0 to 1, and then fx. Again, this is your fx. X minus x squared, and then copy this sine n pi x dx. Okay, do the tabular method, integration by tabular method. X minus x squared, and then for integration sine n pi x. The last answer for an is equal to 4 over n pi cube, 1 minus negative 1 to the power of n. Please continue with the tabular method and then compare your last answer for an. We have the second initial conditions, which is del u over del t. When t equal to 0, it is equal to 2. So meaning that you need to find what is del u over del t. You need to differentiate your u x t. Okay, differentiate this term. Okay. Differentiate u x t, you have del u over del t equal to summation, and from 1 to infinity, you have negative an sine n pi t plus bn n pi cos n pi t dot with sine n pi x. Make sure to differentiate your u respect to t, not respect to x. Okay, just differentiate your t part. Okay, since you have your del u over del t, you can proceed with this substitution. So 2, when t equal to 0. Substitute 0 here. So this one you have negative an sine 0 when t equal to 0 plus bn n pi, okay, n pi cos 0 sine n pi x. Sine 0 is equal to 0. So this is equal to 0. Cos 0 is equal to 1. So 2 is equal to bn n pi sine n pi x. Okay, to find the bn, okay, you cannot just have the bn because you have bn n pi. You have extra n pi. So bn n pi is equal to 2 divided by L, which is equal to 1. Integration 0 to 1. This is your fx. This 2 is your fx. So constant fx is constant 2. So 2. And then you have sine n pi x dx. So to find the bn is equal to 2. Moving this n pi to the right hand side, you have 2 divided by n pi. And then multiply by this 2. So you have 4. Integration 0 to 1 sine n pi x dx. Okay, you can continue with the integration. Simple integration here. You have sine n pi x, so you have cos, negative cos n pi x over n pi. Try to substitute the limit. The last answer for bn is negative 4 over n pi square, negative 1 to the power of n minus 1. And the last answer for u xt, when you substitute all the an and bn, it is equal to summation n from 1 to infinity 4 over n pi cube negative 1, sorry, 1 minus negative 1 to the power of n cos n pi t minus 4 over n pi square negative 1 to the power of n minus 1 sin n pi t, and you need to multiply with cos, sorry, it's not cos, it's sin n pi x. So this is the last answer for example 5.9. Okay, the UXT. That's all for the application of PDE. We just solved 2 examples for the application. We just finished the analytical part of solving PDE. In next video, I will show you how to solve the PDE using numerical method, numerical approach. As usual, the numerical method will be much easier, much simpler compared to this analytical solution. But it just gives you the approximate value, the approximate solution, not the exact solution. Okay? Thank you.